Now we consider the case of constant perturbation, where the perturbation is constant in time. That means it depends only the space coordinate. However, this lasts for a fixed duration, say from 0 to t. In that manner, we can consider it somehow depends the time. So explicitly, it is not a mathematical function of time. However, it lasts for a definite duration in time. Then the probability amplitude for transition from an initial stationary state to a final stationary state, here I have represented it, say CF1 of t. It is nothing other than say CK1 of t, as we have represented earlier. So I will be switching from F to K, or say from K to F. These are only representations. F is in the sense that it is corresponding to final quantum state. If I state you that K corresponds to final quantum state, say an index K corresponds to final quantum state, say I will be writing it as CK1 of t. So CF1 of t is equal to 1 by IH cross, and even I can omit this representation 1 here because I am satisfied with the approximation up to the first order, or the term that I will be evaluating is nothing other than the term which is first order. So I need not specifically represent it as say 1 first order term. That's equal to 1 by IH cross integral from 0 to t h prime fi of r. Right now h prime is independent of time. E raised to I omega fi t prime dt prime, as the integration is over the definite limit 0 to t. The variable I will be representing using the primary index. Now h prime is independent of time, so it can be taken out of this integration in terms of time. H prime divided by IH cross integral from 0 to t e raised to I omega t prime dt prime. This has an integral e raised to I omega t divided by I omega, and in the limit 0 to t. H prime by IH cross e raised to I omega t. T is substituted as the limit. This is omega t pi. Minus e raised to I omega into 0. E raised to 0 is 1 divided by I omega. I into I make it say I square in the denominator, that is minus 1. Minus is written here, minus h prime by h cross omega e raised to I omega t minus 1. So this is the probability or amplitude of transition when the constant perturbation act for a duration equal to t. Now probability of transition is then the square of this probability amplitude. So probability of transition, that is the chance for transition from an initial quantum state to a final quantum state, is amplitude of transition square, modulus square. That is h prime square divided by h cross square omega square. Square of the negative term becomes say positive. E raised to I omega t minus 1 is a complex parameter. So the square has a meaning. If A is a complex parameter, A square means A star complex conjugate of A into A. So this is E raised to I omega t minus 1 complex conjugate into E raised to I omega t minus 1. You open this bracket, E raised to I omega t into e raised to I omega t complex conjugate is e raised to minus I omega t. So e raised to minus I omega t into e raised to I omega t, make it say e raised to 0, that is 1, minus 1 into e raised to minus I omega t minus e raised to minus I omega t. Omega fi is understood. Minus 1 into e raised to I omega fi into t, e raised to I omega fi into t. Minus 1 into minus 1, make it say plus 1. So 1 plus 1, make it 2. Minus is common for both these terms. E raised to I, minus is taken out, e raised to I omega t plus e raised to minus I omega t remains in the bracket. So this is equal to h prime square by h cross square omega square 2 minus This is of the form e raised to I theta plus e raised to minus I theta. That is 2 cos theta. So this is minus 2 cos of omega t. 2 is taken out, 2 h prime square by h cross square omega square into, this is, once 2 is taken out, 1 remains here and cos term remains here. 1 minus cos theta is 2 sin square theta by 2. So 1 minus cos omega t is 2 sin square omega fi into t divided by 2. So the probability of transition is 2 into 2, 4 h prime square by h cross square sin square omega t by 2 divided by omega square. Omega term is written here. I will be applying some fundamental theorems in limits here. So this is the probability for transition. Now we will have to analyze this probability of transition specifically to get some answers to some definite questions. I will not tell you the questions right now, but we will get the answers as the inference of the analysis that we have to follow now. So the probability amplitude of transition is 4h prime square, where h prime kn or h prime fi is the matrix element of transition. As h prime is constant in time, this parameter also will be constant in time divided by h cross square, which is constant, sin square omega t by omega square. Omega is independent of time, so there is only one term that depends on time, which is a square sinusoidal term. Once you plot the variation of the probability of transition with time, where time happens to be the time of exposure, time of interaction. If you are looking into this problem, specifically the case of, say, scattering, then that include the duration for which the target and projectile materials undergo interaction. So time of interaction is taken along the x-axis and the probability is taken. Probability from an initial quantum state to a final quantum state for transition is taken along the y-axis. These are constants for h prime square by h cross square, and this constant line is shown here. That happens to be the peak value of this transition, and the time dependence is in terms of sin square. Sin square will be resembling a sine curve with positive values or in the positive quadrant. So the variation will be following a sinusoidal variation or a square sinusoidal variation, with the peak value of transition oscillating between for h prime square by h cross square and for h prime square by h cross square omega square and 0. So when time t equal to 0, this sin square term will be 0, so the probability is 0. When sin square term has its maximum value, that happen when this angle is pi by 2. That is when omega t divided by 2 is equal to pi by 2. Then this sin omega t by 2 is sin pi by 2, which is 1. When sin pi by 2 is 1, sin square omega t by 2 has its maximum value, say 1 square, which is 1. Then the probability will be maximum and is for h prime square by h cross square omega square. And this corresponds to that duration of time or that instant of time. This instant of time you can evaluate from this equation. 2 vanishes, omega t equal to pi or t equal to pi by omega. So when time equal to pi by omega or in odd multiple of pi by omega fi, the probability will be maximum. Or if you take this angle omega t by 2 equal to pi, then sin pi will be 0. This term sin square omega t by 2 will be vanishing, and the amplitude of transition will be, probability for transition will be 0. So corresponding to this, time can be evaluated as say 2 pi by omega, or any even multiple of 2 pi by omega fi will have a transition probability which is 0. So we make some inferences here. First inference, transition probability do follow a sinusoidal variation. It oscillate between a maximum value for h prime square by h cross square omega square and a minimum value which is 0. When time t is equal to an odd multiple of pi by omega, the transition probability is maximum and is a constant given by 4h prime square by h cross square omega square. That is the second point that we have to make. And the third point, when time of exposure t is an even multiple of 2 pi by omega, or say pi by omega, an even multiple of pi by omega, then there is no question of transition and transition probability is 0. This now make one of our hypotheses or our expectation wrong. We assume that if we expose the system for a prolonged duration, we assume that the transition probability from an initial quantum state to a final quantum state will be increasing largely, but that is not the case. As time increases, the transition probability increases. Soon it reaches a maximum for a duration of time t equal to an odd multiple of pi by omega. After that, it will be falling to a value of 0 when the time of exposure is an even multiple of pi by omega, and in this manner the probability for transition do oscillate between its maximum value for h prime square by h cross square omega square and 0. Of course, there is one more parameter on which the probability do depend. There happens to be omega, that is the angular frequency difference between the initial and the final quantum state, which is in fact a measure of the energy, as we have seen earlier, because E equal to h cross omega. Then omega Fi corresponds to the energy difference between the two quantum states that are connected by means of the transition, or h cross omega Fi is equal to exactly EF, energy of the final quantum state, minus energy of the initial quantum state. If this is negative, this means final quantum state has an energy less than the initial quantum state. That means the transition is a de-excitation transition, and if this magnitude is positive, it means final quantum state has an energy exceeding that of the initial quantum state, and the transition corresponds to an excitation transition. Now, how far this energy difference are possible as long as the probability for transition is concerned? For that, we will have to find a plot between the energy difference of transition and the probability for transition. For that, we have to draw a curve between energy difference of transition or angular frequency difference of transition along the x-axis and the probability for transition p along the y-axis. This plot is shown here. Transition probability and frequency, or frequency difference of transition. We have p equal to 4h prime square by h cross square sine square omega t by 2 by omega square. Now, I have a fundamental theorem in functions limits continuity. Limit theta tends to 0, sin theta by theta equal to 1. I am going to apply this. For that, I'll have to take this angle argument, omega t by 2. I have omega square in the denominator. So I'll be multiplying and dividing this by means of t square by 2. that is t square by 4, t by 2 whole square or t square by 4. Then this becomes 4h prime square by 4h prime square by h cross square sin omega t by 2 by omega t by 2 whole square into 2. Cancel this t square by 4. Let me multiply this also by t square by 4. So 4 vanishes, t square comes here, h prime square t square by h cross square sin omega t by 2 by omega t by 2 whole square. Now suppose we take omega fi, the frequency difference corresponding to transition from an initial quantum state to a final quantum state along the x-axis and the probability of transition along the y-axis. Let this energy difference omega fi is 0. That means there is no question of any transition. That is, as a consequence of this interaction, there occur no transition. The initial quantum state is retained even after the interaction or even after the time-dependent perturbation being lasting for a definite duration. There occur no transition. Then the probability of transition becomes h prime square t square by h cross square sin omega t by 2 by omega t by 2 in the limit t tending to 0. In the limit omega tending to 0. T tending to 0 we have already seen. In the limit omega tending to 0. When omega tends to 0, this term omega t by 2 tends to 0. Then we can apply this limit theta tends to 0, sin theta by theta equal to 1. So that this term will be equal to 1. So that the probability of transition is h prime square t square by h cross square. So when frequency difference of transition is 0, transition probability is found to be h prime square t square divided by h cross square. That is, as the time of exposure increases, the probability of transition corresponding to this case. And what is this case? There occur no transition. So as time of transition increases, there occur no transition, where the probability corresponding to no transition is found to be h prime square t square divided by h cross square. Now, as omega increases, what happens? That is, as omega increases, that is the frequency difference of transition or energy difference of transition increases. This is the initial quantum state and this is the final quantum state for one case. This is the initial quantum state and this is the final quantum state for another case. This energy difference is comparatively lesser than that of this energy difference. And the case that we have already seen, there is only one state, there occur no transition and the probability is found to be, say, h prime square t square by h cross square, which is a square variable function in time. Now, as omega start increasing, sin omega t by 2 by omega t by 2 will be falling. This lasts till omega becomes 2 pi by t. What happens when omega becomes 2 pi by t? We have, say, omega equal to 2 pi by t, then omega t by 2 will be equal to omega t by 2 will be equal to 2 pi by t, 2 pi by t. If you like, you can put pi by t to analyze what happens at this value of pi by t. So, omega t equal to 2 pi by t. Omega equal to 2 pi by t. Then omega t by 2 will be equal to 2 pi by t into t by 2. T vanishes, 2 vanishes. This is equal to pi. So, the argument of sine becomes pi. Sine pi is 0. So that the probability of transition is 0. What happens if omega t by 2 equal to, or omega equal to pi by t? When omega equal to pi by t, omega t by 2 will be equal to omega becomes pi by t into t by 2. That is, t vanishes, this is pi by 2. Sin pi by 2 is 1. So in the numerator you will have 1 and the denominator you will have omega t by 2 whole square. That comes to the numerator to make it say 4 by omega square t square. Then the probability of transition will be h prime square t square into 4 divided by h cross square omega square t square. Omega square t square. T square vanishes. This becomes 4 h prime square by h cross square omega square, which is lesser than h prime square t square by h cross square. The probability amplitude corresponding to no transition is concerned. So the probability amplitude is maximum corresponding to no transition. And as the frequency difference increases, this probability will be falling. Ultimately, the probability of transition is 0 when the frequency difference corresponding to the initial and final quantum states connected by means of the transition is 2 pi by t. After that, it again increases up to a value. Again, this will be falling, say sinusoidally with some damping. For omega difference equal to 4 pi by t, this again becomes 0. Now this resembles a diffraction pattern. This corresponds the primary maxima and this corresponds the secondary minima. And on the basis of this, we make some inferences. The first inference is that the probability amplitude corresponding to no transition is maximum. So probability corresponding to no transition means there occur no transition for most of the atoms. Most of the atom will have an inertia to continue in their own initial quantum states. And this probability corresponding to no transition is directly proportional to the square of time. So you cannot make a transition by increasing the exposure time. Generally, we may think that often do go with the logic. If you are going to heat up a metal for a prolonged time, more and more heat will be conducted through it. So we will have some preliminary thought that if we make the exposure of the system to this perturbation for a prolonged duration, we will be able to account for a larger transition. However, that is not possible. See, mathematically, as we have seen that the probability for no transition is proportional to the square of time. This never tell you that if you increase the time, the probability is increasing. Instead, it is the probability for no transition. So, even if you make a prolonged exposure, there occur no transition because most of the probability corresponding to no transition will be there. For mathematically, we have maximum probability corresponding to no transition. Now the third point, as the energy difference increases rapidly, this will be falling. That is, the probability of transition is falling rapidly as the energy difference or frequency difference between the final and initial quantum state increases. So you will have a comparatively greater transition corresponding to this energy difference comparing with the transition probability corresponding to this larger energy difference. Or we say that transition between adjacent quantum state has greater probability for transition, or most of the transition will be occurring between adjacent quantum state comparing with two quantum states that are placed far away. So the first point is there occur most often, for probability for no transition is maximum. That increases with exposure time as well. As time increases, the probability for no transition is found to be increasing. Now, the second point, as the frequency difference or energy difference increases, the probability for transition is found to be, say, falling. And the probability for transition corresponding to a frequency difference of pi by t is found to be independent of time. It is a constant independent of time, unlike the probability for no transition. Probability for no transition is proportional to the square of time. As you increase the transition exposure time, this probability for no transition also is found to be increasing in a square manner. However, that is not true when the frequency difference is of the order of, say, pi by t. When the frequency difference is pi by t, this is a constant. Probability for transition is 4h prime square by h pro square omega square, which is a constant in time or independent of time. So you cannot account for such a transition also by prolongating the exposure for this perturbed part of the Hamiltonian, or say the perturbation. And corresponding to a frequency difference equal to 2 pi by t or any even multiple of 2 pi by t, the probability for transition is 0. Corresponding to that, you have some secondary minima on the curve, representing the variation of the transition probability as a function of frequency difference of transition or energy difference of transition. Now, the transition can be an excitation or a de-excitation transition. When omega fi is positive, you will be getting this part of the curve. When omega fi is negative, corresponding to a de-excitation transition, you will be getting this secondary minima and secondary maxima on the left side. So, this is the fourth point that we make. When the energy difference is an even multiple of 2 pi by t, corresponding to either excitation or de-excitation, there occur a transition probability that's equal to 0, or there occur no transition corresponding to this energy difference. And the transition probability for an excitation transition is exactly the same as the transition probability for a de-excitation transition, having exactly the same energy difference or frequency difference. If it is an excitation transition, this must be referred to as induced absorption. If it's a de-excitation transition, this needed to be referred to as a stimulated emission. So the transition probability for induced absorption and that for stimulated emission are exactly equal. It is that way you have a curve having this peak value exactly equal to the peak value of the curve in the de-excitation regime. This is referred to as the principle of detailed balance. However, practically this is not correct. This is governed by the distribution of atoms in different quantum states. This distribution will be following, as you know, or as you have learned in statistical mechanics, this distribution will be following the classical Maxwell-Boltzmann statistics. The population of atoms occupying the lower energy states will be comparatively greater than the population of atoms occupying the higher energy state, because the population of atoms in the second quantum state is equal to the population of atoms in the first quantum state into e raised to minus energy difference corresponding to the second and first quantum state delta E divided by kT. So this depends on two different parameters. One, the temperature of the specimen, and the second one, energy difference. As this energy difference increases, this population will be falling exponentially. So if there are 1000 atoms in the first quantum state, you can expect only 100 or 10 atoms in the second quantum state. So since there are more number of atoms occupying the lower energy states, lower stationary states comparing with atoms in the higher energy states, there is scope for more absorption or excitation transition comparing with de-excitation transition. So practically there will be greater probability for excitation or induced absorption rather than